Right. So for the first talk this morning, we have the pleasure to have Barinder, Singh Banwait from Boston University, who will talk to us about towards strong uniformity for isogenies of prime degree. Barinder, all yours.
Okay, thank you. Well, sorry, was that somewhere in the front from the accent? Oh yeah, salut. Okay, well yeah, I can't see anyone, but well, it's. Yeah, I'm very happy to have at this conference. So yeah, I'm going to be speaking about some recent work that I've done with Martin Delix, and yeah, so it's available in the archive at this link. So I'm going to motivate it a bit by talking. So yeah, this talk is going to be about isogenies, but I'm going to first start by talking about a similar story for torsion subgroups. So yeah, what it actually means. I'm going to start back from a theorem that hopefully that I imagine everyone is very familiar with. So namely, if you have an elliptic curve over a number field K, then the group of K rational points on this on E is a finitely generated abelian group. So in particular, it's isomorphic to a finite group called the torsion subgroup, and then finitely many copies of the integers. Yeah, so we're for some R, so we have this isomorphism where R is the rank of the elliptic curve. So I'm not going to say much about the rank here, but rather I'm going to ask what possible torsion subgroups can you get as you do this. Yeah, so historically this was first proved for elliptic curves over Q by Mordell in 1922, and then a few years later generalized to the setting of abelian varieties over number fields by Weil. So yeah, so we're going to take this question, like what possible groups can you get? So yeah, to make this a bit more precise, we're going to fix K and the number field, and then you ask, as you vary over all elliptic curves over K, what possible groups can you get? So this question I'm going to call uniformity of torsion. And this is different. So this is a slightly different question to the following question called strong uniformity of torsion, where you're not fixing K, but you're fixing a degree D, an integer. So you fix a D, and then you allow not just the elliptic curve E to vary, but also your base field to vary. So you're varying over all degree D extensions of Q. So it's like you're varying in like a doubly infinite family, and then you ask what possible groups can you get. So yeah, for D equals 1, these two questions are the same because Q is the only number field over Q of degree 1. And so yeah, in that case, oh yeah, okay. So I was gonna okay. So just a bit of notation in this second question, phi of D is going to denote the possible groups that can arise, and at this point, this could be infinite, but yeah, we'll see very soon that it's finite. Anyway, yeah. So for D equals 1, this is Mazur's famous torsion theorem from 1975. Oh, sorry, 77. Namely that for elliptic curves over Q, you have only one of these 15 possibilities, and moreover, each one occurs infinitely often. So yeah, like this was proved by Mazur in 1977. It was at the time it was known as Ogh's conjecture, although actually it goes back to Beppo-Levi. So Beppo-Levi had stated it. He seems to have stated this conjecture in his 1908 Rome address at the ICM. Yeah, so there's a nice survey paper by René Skov and Norbert Chapaka about this. So yeah, this is what's often quoted as Mazur's torsion theorem. Really, what he did was to prove the following result: that if you have an elliptic curve over Q that admits a Q rational torsion point of prime order P, then P is 2, 3, 5, or 7. And it was already known by results at the time, due to Daniel Kubert, that this was enough. So like once you find a bound on what prime orders can arise for torsion points, then you get Ogh's conjecture. So yeah, at least for d equals 1, this strong uniformity question, it comes down to like just bounding these torsion primes. Yeah, so we're going to call a torsion prime in degree d a prime for which there exists an elliptic curve over some degree d number field that admits a rational, for which there is a torsion point of that prime order. And yeah, so at least in this case, we get this that it comes down to just bounding these primes, but that's unfortunately not quite true in general. So in the early 90s, there's this paper of Kamieni and Mazur, where they are considering this question in general. So it's from this paper that this notation S of D comes from. So S of D is the set of torsion primes in degree D. And yeah, so like at the time it was conjectured that this is finite for every D. So they prove in this paper that like the finiteness of this set S of D is equivalent to finitely many groups arising. Of course, like one implication here is obvious. Like if you have finitely many groups, then clearly you have finitely many primes. But the converse is not obvious. But it's important to note here that even though we know like this equivalence, this is not effective. So even if one can determine exactly the set S of D for a given D, one does not automatically get what possible groups arise for that D, because the proof of this proposition is not effective. It is an application of a result of Faltings from the early 90s that proves a certain case of a conjecture of Lang, to do with abelian subvarieties in varieties, in general varieties. So yeah, so we know that if you can determine finiteness of S of D, then one has we know that the list is finite. So at this point in in this talk, I'm going through this historically a bit. So like at this point, we don't know that S of D is finite, but then yeah, like as is also well known, I think maybe Loic Malel, I saw his name in the program as well. He may be in the audience or there. So yeah, famously he proved that that this is finite, that S of D is finite, and also gave this nice explicit upper bound of D to the 3D squared. So yeah, I mean it is like exponential there in D, and this was improved subsequently pretty quickly, I understand, already in the same year by Österle to this bound, which is I believe this is the best known unconditional bound. So 1 plus 3 to the D over 2 all squared. So this was unpublished at the time, but appears as an appendix to chapter 3 of Martin's PhD thesis. So even though we have this general bound in degree D, the true, like for a given D, the actual set tends to be much smaller. So the latest on what's actually known for like values of D, for given values of D is this theorem due to these people shown below. So yeah, S of 1 was Mazur, S of 2 was Kamieni, S of 3 was Parent, and then 4, 5, 6, and 7 was done by this paper of Dedix, Kamieni, Stein, and Stahl. And then very recently, Malia Kawaja, who's a student of Samet Siksek at Warwick, she is determined S of 8. So yeah, like even though, like say, if you plug in D equals 8 into this, you're going to get something much larger than 23. Anyway, yeah. So I think it's also like an open problem about like, or I guess there is an expectation that the true bound here should be linear in D, but yeah, that's like a major open problem, I guess. So Yeah, anyway, so I was talking about these groups, like actually determining the torsion groups. So what's known on that front? Yeah, so phi of 1 was Maser's result, these 15 groups. We also know what yeah, so we know S of 2, and so that doesn't automatically give you phi of 2. There's still quite a bit more work to do there, but yeah, so that was determined finally in one of Kamieni's papers in the so I guess this result came from like it was finally proved by this paper of Kamieni in 92 Invenciones, building on work of Kenko and Momoza, a series of papers of Kenko and Momoza in the 80s, and then very recently, like phi of 3 has been determined also by work of Martin with Etropolsky, Van Hoy, Murrow, and Zurich Brown. No one also gets 26 groups in this case, but a different list of 23 groups. But yeah, so that's the state of the art of phi of n. So even phi of 4, the exact list, the full list is not known. It is known what groups arise infinitely often. I think that's known for degrees up to 7, maybe. But yeah, like what is phi of 4? That's like that is yet to be fully determined. Anyway, yeah. So far, I've been speaking about mostly strong uniformity for torsion, where you fix the degree. But I also mentioned this other question of uniformity of torsion, where you're not fixing the degree, but you're fixing a number field, and then you're asking what possible torsion subgroups do you get. So this question seems to have first been asked by Philip Neumann about just over 10 years ago. So he was doing this for the cyclotomic quadratic fields. So for Q adjoin root -3, and for Q adjoin I, so he was able to determine. So like in both of these cases, the list of groups has to be a subset of the Kamieni-Kenko-Momoza list. And then the question is, so he was able to show that like in this top case, you get one of the lists in Maser's, one of Maser's 15 groups, or these other ones here, and then similarly for I. And so so right now I'm actually in Zagreb, and later today I'm going to be talking about a different piece of work with Martin, where we do this for all quadratic fields Q adjoin square root of D, where the modulus of D is less than 500. But yeah, anyway, so that was like a story for like that's what's going on with torsion subgroups for elliptic curves over number fields. I now want to switch over to isogenies a bit. So yeah, for isogenies, so like if you have a torsion point of prime order P, then the group it generates is going to be Galois stable. I mean, it's going to be pointwise fixed, and that's going to give you a subgroup of order P. That can then, you can think of that as the kernel of some k-rational P isogeny, and there is essentially like a correspondence between isogenies and their kernels. So you can then start asking a similar question for isogenies. So you can fix a number field K, and then you can ask what possible primes arise as the degree of a k-rational isogeny as E varies over all elliptic curves over that K. So I'm going to call this set I sub prime deg of K. So if you have uniformity, you can also ask strong uniformity, where we're not going to fix K, but you fix a degree D, and then you vary over all elliptic curves over degree D number fields, and then you ask what possible primes can arise from this. So these so-called these we're going to call isogeny primes. Again, for D equals 1, this is a theorem of Maser in 78, where he showed that you can only have these 12 prime numbers for Q. So when I started my PhD thesis, John Cremona, who's my advisor, he got me thinking about possibly extending this to other number fields. So like such an exact determination had not been done for any other number field. Before going on though, like it's one has to say something about CM fairly quickly, because it's fairly easy to, it's well known that one can make this set infinite, and so that one can get infinitely many isogeny primes from CM elliptic curves. So if E is an elliptic curve over some number field K that has CM that's defined over K, you want these extra endomorphisms to actually be defined over K. Then any prime that splits or ramifies in the corresponding CM ring, that's going to be an endomorphism of a degree P and hence an isogeny. And so this set is infinite, like infinitely many primes are going to split. Like about half of them. So this is like one easy way of getting infinitely many primes. And in general, these isogenies that you construct in this way are going to be defined over the Hilbert class field of your imaginary quadratic field here. So yeah, if your base field contains this, then you're going to get infinitely many primes. So if you assume G at H, then the converse of this is also true. So that comes from putting together a paper of a theorem of Mimosas from the 90s, together with Morel's uniform boundedness, the theorem that we mentioned in the previous section. And I'll say a little bit. I think I'll say a little bit more about this work of Mimosa later. So anyway, after this, so you can ask this question. If you assume GIH, then you take a number field not containing the Hilbert class field of an imaginary quadratic field. So then this set is finite, and then you can ask, what is it? Like, what like, can you actually determine it in any cases? And yeah, so I started thinking about this a few years ago, and so I found the first instances of this for quadratic fields. And then I started working with Martin Didik's, extending this to a general number field. And so like here we have some examples of cubic number fields whose isogeny primes we're able to determine. But yeah, that's about uniformity. But now, what about strong uniformity? So this is really what my talk is about, and yeah, so what the rest of the talk is about. So again, because of the CM thing, this can't be true in general. But so you can ask this question, and this question is still open. So yeah, so you fix a D, and then you ask what possible primes arise as isogeny primes as you vary over elliptic curves, all elliptic curves over all degree D number fields, but you're specifically excluding these isogenies that are arising from the CM construction that I mentioned in one of the previous slides. So this has a hope of being finite. It's still not known to be finite for any D apart from one. I want to emphasize this is an open problem still. If however D is odd, then one can actually remove this, because like if you have an elliptic curve over an odd degree number field, well then it's never going to contain these CM isogenies that are rational over K itself. It might have like potential CM, but as far as this question is concerned, that's okay. So we call this question isogeny Morel after Pete Clark. So I think Pete Clark coined this phrase because it's like the isogeny version of what Morel did for torsion. And yeah, so before going on, again, I want to emphasize we have not solved this. This is still an open problem. But so what Martin and I do, and what I'm talking about here, is that we establish this for isogenies whose signature that I'll talk about in the next section. So yeah, we establish this based on some conditions on the signature of an isogeny. And so that's what I'm going to start talking about next. But maybe now is like a good time to stop and ask if anyone has any questions.
No, I think all right.
Okay, all right. So, okay, so this phrase goes back to this a paper of Freitas and Zigzag from about 10 years ago. Yes, I think they were criteria for irreducibility of mod P Galois representations. They were, so they're applying this to, so they're applying the modular method to some cases of the generalized Fermat equation. And when one is doing the modular method, there are times when you want your so you want your Frey curves to have irreducible Galois representation mod P, and so that's why they were interested in this. So yeah, this isogeny signature is something that you associate to the character of the isogeny. So what's that? So this is just this is the one-dimensional Galois representation you get when you consider the Galois action on the kernel of the isogeny. Yes, this is often called lambda. So even though it's like we define it as a Galois character, by class field theory you can associate. You can also think of this as a character on the group of ideals of K co-prime to P. We're more careful about this in the paper, but like in this talk, I'm just going to equate. For simplicity, I'm just going to use the same notation for both of these things. So yeah, there is this. Yeah, so I need to recall a certain key result, which expresses how the 12th power of this lambda is acting on principal ideals. With this class field theoretic notation. So there's quite a lot going on in this proposition. So I've broken it down. So K is going to be a number field. Big K is Galois closure. And I'm going to let sigma be the embeddings, the set of embeddings from little k into big K, into C equivalently into big K. Lambda is going to be a P isogeny character. So if you frac P0 is going to be a choice of a prime ideal above P in big K. So let's make this choice. Then with that, having made that choice, there is then one can define this formal sum over the embeddings with these weights A sigma. These A sigmas have to be there's only 5 options for A sigma: 0, 4, 6, 8, or 12. And this formal sum epsilon has the meaning, the interpretation that for every alpha, so for every element of K, for every element of K co-prime to P, the 12th power of lambda, how does it act on this principal ideal? It acts via alpha to the epsilon. So this is, unfortunately, I didn't write the definition of this on the slide. So this is a twisted norm. It's like the product of sigma of alpha for sigma in big sigma, but you're twisting, but then you raise it to the power associated to A sigma. So it's like, I mean, does this annotation work? Let's see if this works. What's it going to be? Product sigma. I'm just doing this on my laptop trackpad. So it's not great. Sigma alpha, and then what is it? A sigma. Yeah, I guess this is why people have iPads. Should get an iPad. Does this work? Can people see that? Is that okay? Anyway, it's a twisted norm. It's a twisted norm. And so, moreover, if P is large enough and unramified in K, then for every such choice of this frac P0, this signature is unique. So yeah, so this was first proved by Mimosa in this paper that I mentioned earlier, under some conditions, namely that K is Galois and P is unramified, and then a more rigorous treatment was given by Agnès David in her earlier in some of her early work, and so what Martin and I do in our previous work, the one about uniformity of isogenies, we were able to generalize this result to the non-Galois case and for P ramifying in K. So yeah, I'm going to need this. I'm going to need this result a bit later. But like it's this formal sum epsilon. This is what the this is what we call the isogeny signature. It looks like this thing is still here. So do I just clear all drawings? Yeah, there we go. Let's get rid of this. Yeah. Anyway, so this epsilon is the isogeny signature. Specifically, we have made a choice here of a prime ideal, but one can show that a different choice, like it just permutes these a sigma integers, which for us is not going to matter in the end. So we're just going to drop it from the notation. But more concretely, like if you fix an ordering to these embeddings, it allows you to really concretely regard this signature as a d tuple of integers valued in this set of 5 elements. And behind the scenes, so yeah, like this statement doesn't tell you what these integers are. It just says that like they exist. Really, what's happening behind the scenes is that one is defining an integer a sub p for a prime ideal of k, and this tells you how far lambda to the 12 is from being unramified. So it's known that lambda to the 12 is unramified away from p. So that goes back to this paper of Serre in 1972, Propriétés galoisiennes des points d'ordre fini de courbe elliptique, and ramification at p that's expressed by this power, a certain power of the mod p cyclotomic character. And so that's what these APs are, and from that you can define the a sigma, because then you have a Galois action on the prime ideals of k over p. In particular, if all of these integers happen to be 0, then lambda to the 12 is unramified everywhere. Anyway, so okay, the upshot, like if you've never seen signature before, so it's it's a d. So you could just concretely think of it as a d tuple of integers, valued in 0, 4, 6, 8, or 12. So in particular, for a given degree d, there's only 5 to the d of them. And yeah, this depends on a choice of ordering of the embeddings, and it's telling you how inertia at p acts on the kernel of the isogeny. So yeah, like this problem that we're considering here, isogeny morale, if you can bound. So yeah, we care about all isogenies, but we just said that every isogeny has a signature associated to it, and there's only 5 to the d signatures. So if you can bound for the isogeny primes for isogenies falling in any one of these 5 to the d signatures, then you're done. So like the problem breaks down into dealing with isogenies of a given signature. So yeah, before going on to what we've actually done in this final section, just one final definition. So out of these 5 to the d signatures, some of them have been sort of identified. So these definitions come from Mimosa's paper that was somehow like more problematic, let's say, or require special attention. So if all of them are 0 or all of them are 12, then that's where epsilon, the signature, is said to be of type 1. Yeah, so again, this naming here goes back to Mimosa's paper. If all these integers are 6, then we say epsilon, the signature is of type 2. There is a type 3 as well, but for simplicity, I'm not going to say anything about that. Actually, type 3, that can only arise if K contains the Hilbert class field of an imaginary quadratic field, and yeah, okay, that doesn't imply that those isogenies of CM type. Anyway, because I'm not saying I'm not giving the definition. I'm not gonna go further into type 3 here. I'm going to define the trace. So like the trace of a signature is just the sum of the integers inside that. So yeah, so here it's going to be 0, and this is going to be 12D, and this is going to be 6D. So observe, yeah. So the trace has the trace is an integer, and it has to satisfy one of the following conditions. So either it's not 0 modulo 6, if it is 0 modulo 6, then it's either 0 mod 12 or 6 mod 12. So yeah, I mean, this, yeah, like you might be, yeah, so like you might be wondering why am I saying, why have I said this? Like, yeah, like, this is obvious, and it's to put into context what exactly we have done. So we are able to determine isogeny. So yeah, we are able to uniformly bound isogeny primes whose signatures satisfy this first condition. We can do the second condition as well under assuming GRH. And yeah, so like I said, the problem that we're considering is still open. So like we have not dealt with all cases. In this final case is what we can't do. But we can deal with a special case of this last case. So, like, if epsilon is of type 1, then then the trace is going to be divisible by 12. We can deal with that case. But in all other cases of this final where the trace is 0 mod 12, that's where isogeny Morel, the problem of isogeny Morel is still open. So yeah, let me go into some of the details of how we're getting these results. So that key proposition from the previous. Oh yeah. Okay, I can click here. Yeah. So this key proposition that we had, it implies the following, and this is really like the main algorithmic part of our paper, of our work. So again, I'm going to try to step through this a bit slowly. So yeah, if lambda is going to be a p, so k again a number field, and lambda a p isogeny character, and we're going to take so we're going to take some element of k that we assume co-prime to p. We're going to then consider the fractional ideal generated by this alpha. So this is going to have some factorization in k. So R is going to be the number. R is going to be the number of distinct prime ideals above that divide alpha, and then you have these EIs and FIs. So FI is going to be the residue degree of this frac QI. So okay, so then for each of these distinct prime ideals QI, there exists this beta I in a certain finite set. So yeah, what is this finite set? So it's essentially just the Frobenius roots for elliptic curves over the residue field of QI. So by Frobenius root I mean roots of the characteristic polynomial of Frobenius. So that this is going to be like x squared minus ax plus q to the fi, where a, the modulus of a is between is bounded by 2 times the square root of the norm, the residue field degree. So I guess that's q to the fi over 2. Anyway, so what one can explicitly write down these Frobenius roots, and just think of this set S as the Frobenius roots. We're also putting in plus minus 1 or plus minus the norm of QI, norm of frac QI. So that's So if qi is the prime underneath that, that's going to be qi to the fi. Anyway, point is it's a finite set. For each of these prime ideals, there is this finite set of possible algebraic numbers, algebraic integers, for which tell you what possible values the Frobenius at qi has under this isogeny character. So it's giving you like these possible Frobenius values, and from that one can from this equation one can determine, and taking norms down to q, one can obtain this divisibility. So if I had a blackboard, I'd go into this a bit more. So like if you take this equation to the power of 12, then you get lambda to the 12 of Frobenius. But then that's where the key proposition is coming in, because the key proposition told you how lambda to the 12 acts on principal ideals. And namely that it's being expressed by a twisted norm. So if we do lambda to the 12 of this, and then put together the information from all of these different q's, we then get lambda to the 12 of alpha. So that's but then that's alpha to the epsilon, this result is saying that Frobenius acts as beta I. So then we get this product here. So this integer arises from this previous equation plus the key proposition from this section, the one that was first proved by Mimosa. And then taking norms down to q, one has this integer. So p then has to divide this integer. The problem is then that this might be 0. So this might not tell you anything, and that's what we're going to have to deal with. So from this proposition, like what we want to get something that depends only on d and not on k, whereas this depends quite a lot on what's happening in k. Like how is a certain ideal factoring in k? So what we're first going to do is apply this. We're going to apply this proposition, taking alpha to be a rational prime, like 7. So we're going to call that q. So it's actually in q. It is in z. And we want something that is independent of how that ideal is going to split inside any degree d number field. So this is what I mean here by we loop over all possible splittings of q in a degree d number field. So it's like you're only going to have at most d possible different prime ideals. So like r is going to be some integer between 1 and d, and then the EIs and the FIs will have to be like values such that like EI FI, the sum of this is equal to d. So this is one way of getting rid of the dependence of k, by applying this for alpha something in q and then looping over possible splittings. And then, so for whenever one does this, one's going to generate a whole quite a large set of different beta integers, and we're just going to keep taking the LCMs of these. So that's then what's going on in this key algorithm in the paper, algorithm 4.1. So again, you can see this paper on the archive. So this algorithm has input an integer d, a signature, and a rational prime, and then it's going to compute two integers, b epsilon q and a star. So it's applying this proposition with what I've been saying here, and so like this is all implemented in in the code base that hopefully I'll have time at the end to give a quick demo of. So here, yeah, so here you can see it's determining these splitting types, and we're looping over each of these, and then we're taking these LCMs. It's like a growing LCM that's happening here. So yeah, this integer might be 0. What's happening in this? So what is the star integer? Like, so this is like the non-zero part of this. Like, if any of these integers here are 0, then we don't add that into the LCM. So like, and this is going to be important for one of our results. Like, we need to know the non-zero part of this integer. Anyway, so the point of all of this is that given this input information, we can determine an integer that is a multiplicative bound for isogeny primes of that signature, but it might be 0, and if it's 0, well then like it's not telling you anything. In practice, also we're going to do this for many different queues and then take a GCD to sort of try to get a smaller bound. Like for one value of q, this could be enormous, but if you start taking several of them and take a GCD, then you're able to get it to be smaller. So yeah, from this, one can deal with the first case where the trace is not divisible by 6. So like none of these integers are going to be 0, and yeah, so like if you know that this is non-zero, then that's great. You've like dealt with that case, and one can quite easily show that like none of these integers are going to be 0. In this case, so yeah, if one of them was 0 for some beta, well then by definition that means we're going to have this equality. So q to the trace, and the reason we're getting trace here now is because we're taking alpha to be q itself. So the norm is so that twisted norm, we're taking the product over sigma of alpha, but if alpha's in the base field, well then that's just going to be alpha itself, and so that's why we're going to get alpha to the sum of the integers in this twisted norm. But what are the possible values of the modulus of beta I? So again, like it's either a Frobenius root, in which case it's the square root of q to the fi, or like recall I had this plus minus 1 or plus minus q to the fi. So these are the only possible values for the modulus of beta I, and then like we're conveniently raising to the 12 here. So we see like in every case 6 has to divide the trace if you have 0 here. So taking the contrapositive, if 6 doesn't divide the trace, then none of these are 0, and we then get a non-zero bound. Yeah, so we get this result. So this integer is not 0, and it is a multiplicative bound for these isogeny primes. And once you've got this bound, you can then determine an additive bound of a nice form. And yeah, so this is a huge number. So it's like doubly exponential here, unfortunately, but it's an explicit bound, depending only on D. So yeah, that deals with this first case. The second case, yeah. So I'm just going to give a quick sketch of this one. So in the 6 mod 12 case, so here one can show that if this integer is 0, and if p does not divide this non-zero part, this b star integer, then one can show that p has to split in this imaginary quadratic field, q to the square root of minus q, where q is this choice of auxiliary prime. Now, using effective Chebyshев density, you can find a q for which p does not split in this field, and you can bound you can bound the norm. You can bound that Q. So you can definitely find a Q bounded by 4 log p plus 10 squared, and this is using GRH. So this is using Bach and Sorensen's version of effective Shebatov density. That is like totally explicit. It doesn't have unknown constants in it. But for this Q, because P does not split in this, then we know that P has to divide this integer. And then again, when you have this divisibility, you get this doubly exponential. You get this large additive bound. But then these two inequalities are in contradiction for sufficiently large P. Like, even though this is doubly exponential, the idea is that like Q is something that you're fixing, it's bounded by this logarithm in P, and then that allows you to get finiteness of P, and you can be very explicit about like what actually that bound is, and you get yet larger constants coming in here, but again it's still explicit. And you have to assume GRH for this. If you don't, if you replace this with the best possible unconditional version, then you don't get a contradiction for large P. Okay, and so that's the first two subcases. Now, for the case where 12 divides the trace, that's the open case. We can't deal with that, apart from the case where the signature is of type 1, meaning that either all of them are 0 or all of them are 12. If all of them are 12, then it turns out that considering the dual isogeny will have all of them 0. And so you only really need to we can consider isogenies up to their dual because they're going to have the same degree. So without loss of generality, in this case, we're going to take epsilon to just be all zeros. And again, we're again going to try to play this game. Like, if one of these integers is 0, then what's happening? Because that's really the problem. Like, if we knew that these integers were non-zero, then yeah, we'd be done. But anyway, so if one of these is 0, then in this case, the product of these beta i's is just gonna be 1. For some splitting type here. The only way this can happen is if all of these betas are plus minus 1. But because the Frobenius roots just have norm that is too large. So from that we get that Frobenius acts under lambda squared is congruent to 1 modulo P. And we want to reduce to the case where, so if you had so E is the elliptic curve whose isogeny character is lambda. I want to get to the case where E has potentially multiplicative reduction. But if E had potentially good reduction, then lambda of Frobenius will be congruent to some actual root. It will be congruent to some beta I, so some root of Frobenius, a root of characteristic polynomial of Frobenius, whose norm will be q to the fi over 2. And so again, from before, we'll be able to get some bound in that case. And so we can deal with that. So henceforth, we're going to assume that E has potentially multiplicative reduction at all of these primes qi above this choice of auxiliary prime. And yeah, so this is like the difficult case here. This means that, yeah, so on the corresponding modular curve x0 p, so E with this isogeny is then defining a k rational point on x0 p. The statement that E has potentially multiplicative reduction is saying that when you reduce modulo qi, x has to specialize to one of these cusps, of which there is only 2, 0 and infinity. And these two cusps behave differently. So if the point reduced to 0 at one of the at some prime ideal Q I, then one can show that this Frobenius under lambda squared, well, Frobenius under lambda is going to act as the norm of your prime ideal, and then so putting these two together, you again get a non-trivial multiplicative bound. So then the hard case is when all of them reduce to the infinite cusp. I probably should have said that this whole methodology, it really goes back to Mazur's 78 paper, but so some of these results on what's happening in the difference of the two cusps that you'll find in Kamieni's, one of his, I think it might be that 92 paper of his that I mentioned earlier. So otherwise X reduces to, it specializes to infinity to the D. And so this is precisely the Kamieni-Mazur formal immersion setup. And so, this is in contradiction of a certain map from X0, from X0 P into ultimately the winding quotient, I suppose these days, is not a formal immersion. And then it's known explicitly and algorithmically by work of Derrick's Kamieni-Stein-Stahl, which P's you do not have a formal immersion. So like P divides a certain integer that I'm calling bad formal immersion D. Anyway, this type 1 case is it's really an application of the ultimately Mazur's formal immersion method. So then P, so in this case we have that P has to divide, putting all these integers together, we get P has to divide this, and then again you can get an explicit upper bound, like this. So I'm actually, I think I only have 5 more minutes left, so I'm not going to be able to get through everything here because I also wanted to quickly show the code. But I will give this result. So a corollary of the previous slide gives you a generalization of Morel's theorem that was mentioned right at the beginning. So if you have an elliptic curve over a degree number field that attains a torsion point of prime order, rational over an extension that is unramified at all primes above P, so like unramified torsion point, we are able to bound the P's in that case. And Morel's theorem is like it is like a sort of case of this, where the extension of K is just K itself, which is certainly unramified, or which certainly satisfies this condition. So just quickly the proof, like if L is this extension over which you have this point, capital P, so say L is assumed unramified at all primes above P. By taking the Galois closure, we can assume this is Galois. If this subgroup is K rational, well then we're going to have, because of the statement that it's unramified at all primes above P, that is precisely saying that the isogeny of type 1. So you get a K isogeny of type 1, and so the previous bound applies. If it's not K rational, well then P and sigma P are going to generate the P torsion. This implies that as L contains C to P, so considering ramification, we get this bound. We also get a bound on P, a much smaller one. But in any case, so we get this result. So everything I've said up to now is just about getting bounds. You can then ask, like, we have bounds, but really we care about what the actual numbers are themselves. So this is just quite. This is the same result from a few slides ago. In the degree 2 case, though, we do a bit more work to actually get what the list is. So if you set D equal to 2, you're going to get some huge bound here, but actually we're able to say that these are the primes you get. So type 1 isogenies in the quadratic case, the isogeny primes that you get have to be one of these 11 primes, I think. Yeah. Okay, so I'm going to quickly show the code for this. So if I come to this, I'm going to quickly SSH into Lovelace. Can people see this command line, this command window? Yep. Okay, I'm just going to now go to. So the code you'll find on GitHub. So you go to isogeny primes. Isogeny primes. So you then you check this out. So git clone. So git clone. And then paste this. Okay, so now I have isogeny primes. Okay, so it's this. So this is building on Martin and mine and our previous work, which is about the uniform stuff. But yeah, so we've added this strong uniform mode, which is what I've just been talking about here. So I'm just going to do typical cases, copy this, and then. Yeah, so say uniform isogeny primes. So you just give it a degree. Let's do 2. So let's do that. And yeah, so it runs through the cases that we can deal with for type 1. So we haven't implemented the improvement for degree d equals 2 here. But yeah, so it will determine an explicit superset in each of these for each of these trace values. I haven't done it for d equals 4 in a while, but yeah, there you go. So it runs through all of them, and yeah, it doesn't actually take that long. So yeah, anyway, so yeah, I just wanted to show that quickly, and yeah, so I guess that's the end of my talk. Yeah, thank you very much.